if I asked you to describe the North Sea, you'd probably picture oil platforms, maybe wind farms, lots of pipelines, and maybe some, very sturdy fishing trawlers. It's an incredibly busy, heavily engineered body of water.
Exactly. We tend to see it as this modern industrial hub, right? But underneath all that human activity, and I mean deep beneath the seafloor, the ground is, well, fundamentally defying our expectations. There are geological forces at work down there that are colossal, ancient, and honestly sometimes pretty baffling.
Okay, let's unpack this reality a bit. Our mission today for this deep dive is really looking into the North Sea as a genuine collision zone. We're looking at where these astonishing ancient phenomena, specifically these massive geological structures that are literally upside down meet, cutting-edge modern energy infrastructure, and critical environmental concerns too.
Yeah, we've been digging through the latest seismic conference proceedings and some really detailed ecological reports, trying to extract the key insights. And we're focusing on two distinct but definitely linked realities. First, these massive, kind of bizarre geological structures known as Sinkites. And second, the surprising ecological influence, or sometimes actually the lack of influence, of all the human infrastructure that's now sitting out there.
So it's a journey from, 10 million years ago right up to the latest climate models? Let's start with the really weird stuff. This anomaly known as reverse stratigraphy. When we talk about these massive submerged sand bodies called Sinkites, what does it actually mean to say the geology is reversed?
Well, what's fascinating here is that the fundamental law of normal stratification is essentially flipped on its head. Generally speaking, in geology, newer material settles on top of older material. It's intuitive, like stacking books, right? The last book you put down is always on top.
Right. Simple
Yeah.
enough.
But with Sinkites, we have these layers of newer, heavy sand that have actually sunk down. They appear hundreds of meters below softer, older layers of light sediment. Now, reverse stratigraphy itself is known scientifically, it happens, but finding it on the sheer immense scale we see under the North Sea, that's what makes it so exceptionally rare.
And when we say immense, the scale really does defy visualization sometimes. The reports confirm hundreds of these structures, each potentially hundreds of meters high, kilometers wide, and running for tens of kilometers long beneath the seabed. That's not just some local anomaly. That sounds like a fundamental feature of the whole regional geology.
Absolutely. And the research team actually coined the term sinkite to reflect this process, these heavy sand layers that somehow behaved like a fluid and literally sank, driving the structure downward. The dating places their formation somewhere between the late Miocene and Pliocene periods, so that's roughly 10, down to about 1.6 million years ago.
Wow. So we're talking about structures that are way older than our species. But how did this giant million-year-long geological swap meet even begin? What was the mechanism? How did sand and soft mud layers actually exchange places like that?
The primary driver was what's called buoyancy-driven instability, coupled with some kind of catastrophic trigger. You had this lighter material, what the researchers call ooze rafts, essentially fine mud layers made of tiny marine fossils sitting beneath a much heavier layer of sand.
Okay, so heavy on top of light.
Yeah.
Like trying to balance a brick on a bowl of pudding, maybe?
Precisely, a perfect analogy. That situation is inherently unstable. The trigger was likely sudden underground shifts. Could have been ancient massive earthquakes or maybe extreme pressure changes from the shifting land masses around the North Sea basin. This instability caused the heavy sand layer to rapidly lose its rigidity. It's a process called liquefaction.
Ah, liquefaction.
Yeah, it basically allowed the sand to funnel down along natural fractures or weaknesses in the underlying rock layers.
So the sand momentarily behaved like quicksand, but on a truly monumental scale, sinking hundreds of meters down. And, okay, as the heavy sand sank, it must have displaced something, right? What happened to the lighter stuff it pushed out of the way?
Right, that lighter material, those ooze rafts, was essentially squeezed upward in response to that tremendous pressure. And that formed the counterpart structures, which they've called floatites. It's a completely inverted geological model. The heavy stuff sinks, the light stuff floats up.
Okay, here's where it gets really interesting and connects right back to the present day. Why should modern energy companies, care about a geological event that happened 10 million years ago? Seems pretty distant.
Well, this raises an absolutely essential strategic point now. These aren't just static, solidified masses from the past. We are now increasingly relying on the subsurface of the North Sea for critical new energy goals, primarily carbon capture and storage, or CCS. We're planning to inject massive volumes of CO2 deep into the ground for hopefully very long-term storage.
And the CO2, once it's captured and pressurized, that becomes the fluid in this whole underground scenario.
Exactly. So understanding the precise configuration and crucially the potential pathways within these massive fractured Sinkite structures, it becomes vital for critical risk management. We absolutely need to know where that CO2, that fluid, will move over potentially thousands of years. If the ancient geological plumbing involves this kind of massive inverted faulting and fracturing, it completely changes how you model the security, the long-term viability of a CCS project. These structures basically dictate whether the CO2 stays trapped safely or finds unexpected escape routes.
That makes perfect sense. Wow. Okay, so to even map something so vast, so deep and structurally complex, I mean, miles beneath the seafloor, millions of years old, that requires a serious, next generation upgrade in technology, surely. How on earth did geophysicists even see these formations?
That's the perfect transition point. The imaging technology has had to become exponentially more sophisticated just to deal with this complexity. Today, the foundation of this kind of research relies heavily on much denser data acquisition, using things like ocean bottom nodes or OBN.
Right, so instead of just towing cables behind a ship, they're actually dropping hundreds or maybe thousands of sensors directly onto the seabed itself to listen to the return signals.
Correct, a much richer data set. But that raw OBN data is just the start. The next step is the processing, and this is where we hit some genuine breakthroughs in recent years. Techniques like Marchenko redatuming, sometimes called autofocusing.
Okay, Marchenko redatuming. That sounds like pretty serious jargon, so let's simplify. What's the practical impact? What can you actually see now with this technique that you couldn't before?
Well, think of it this way. When seismic waves travel deep underground, they bounce off everything the seafloor, different rock layers, and they even bounce off each other multiple times. These multiple reflections, or multiples, are usually just noise that clutters up the image, making it really difficult, sometimes impossible, to see the deep targets, like a Sinkite structure, clearly.
Ah, okay. Like trying to hold a conversation in a room with a really bad echo. You just hear the jumble.
That's a perfect analogy.
Yeah.
Marchenko redatuming uses highly advanced mathematics to actually treat that echo, that noise, not as something to just discard, but as useful information. It essentially estimates those complex wave fields, including the multiples, and then it attenuates or dampens the spurious arrivals caused by them. This allows the geophysicist to electronically autofocus the seismic energy directly onto the target structure they care about, even if it's hidden deep beneath a highly reflective layer, like salt or basalt.
So it's almost like noise-canceling headphones, but for seismic data, allowing them to reveal these clear, coherent features deep down, features that standard imaging might completely miss because of all the reflective interference above.
Precisely. That's a great way to put it. And if Marchenko redatuming is the autofocus, the next major technique, which is heavily cited throughout the conference proceedings we looked at, is full waveform inversion, or FWI.
FWI. Okay, give us the elevator pitch on FWI. What does that do?
FWI is probably the closest thing we have right now to a geological MRI or maybe a CT scan. Instead of just looking at the timing of when a sound wave returns, FWI uses every tiny bit of the wave energy, the full waveform, the shape, the amplitude, everything, to build an ultra-high-resolution velocity model of the subsurface. It essentially creates a detailed 3D map of how fast sound travels through every single type of rock and sediment down there.
And because sound travels differently through, say, fractured rock versus solid chalk, or through fluid-filled pores versus dry rock, that map tells you pretty precisely what's actually down there, right? The physical property.
Exactly. This lets them characterize incredibly complex or dense materials like the North Sea chalk formation with unprecedented fidelity, right down to seeing small fractures or subtle boundaries where fluids might be present. Both Marchenko and FWI are becoming essential tools for the kind of accuracy needed for today's high-stakes exploration and, importantly, monitoring projects.
And this high-fidelity subsurface characterization, that's vital for environmental monitoring too, right? Particularly for those CCS projects we mentioned earlier.
Yes, definitely. For example, 4D seismic, which is basically time-lapse monitoring using repeated seismic surveys, is being actively used at major CCS injection sites, places like the Northern Lights project and the Endurance CO2 store. You take an initial seismic image before injection, then you inject the CO2, and then you take another image, maybe months or years later. That difference, the 4D aspect, allows them to literally track the plume of CO2 underground and make sure it's behaving as expected, staying exactly where it's supposed to be, safely trapped deep down.
So the imaging technology is clearly incredible. But is all this complex data actually translating into practical, real-world decisions out there on the surface? Is it changing how things are done?
Absolutely. The integration of all this tech is definitely shifting toward highly practical, data-driven applications. Machine learning, for instance, is now being deployed more routinely. One example is using it to automatically analyze side-scan sonar images to identify and map boulder fields on the seabed. Now, that might sound mundane, but it's absolutely critical information for planning the placement and ensuring the stability of structures for offshore wind farm development. It's all about minimizing risk and maximizing efficiency based on really accurate data.
It's a fascinating look at the technology being used to map both the deep past and the future of energy in the North Sea. Now let's pivot a bit. Let's move from those unseen depths to the very visible reality on the surface, the ecosystem impact. All that infrastructure the North Sea is now home to, the platforms, pipelines, cables, wind turbines. What's their effect?
Right. This is where we can look at the really interesting study conducted by CFIS, that's the Center for Environment, Fisheries and Aquaculture Science. They did this work for the InSight program, and it resulted in a comprehensive report using what they call coupled spatial modeling, or the COSM report.
Okay, COSM. And they weren't just like counting fish around platforms, were they? It sounds like they were trying to quantify the effects across the entire food web over a massive area.
That's exactly right. They used pretty sophisticated statistical and ecological models, specifically things called generalized additive models, GAMS, and also ecospace models. They really had to use these advanced statistical methods because the effect isn't simple. You can't just say, oh, more infrastructure automatically equals more fish. The relationship is highly specific. It's nuanced. They had to look for statistical associations that aren't immediately obvious if you just look at the raw survey counts. You need the models to pull out the signal from the noise.
Okay, so it sounds like they were looking for hidden preferences almost. What the marine life really thought about all this human stuff. So what were the major aha moments? Which structures turned out to be the most surprising magnets for life, or maybe deterrents?
Well, the linear structures, things like cables and pipelines, provided some of the clearest positive associations. It turns out that fish, rays, and sharks occurred statistically more often near cables and pipelines than you'd expect just by chance. The thinking is these likely act as sort of corridors or navigational guides, maybe even low-lying shelter, in what is often a vast, relatively featureless, sandy or muddy environment.
So if you're a ray maybe looking for shelter or just a feature to orient yourself, a long pipeline provides a reliable, fixed thing on the seabed. Interesting. But the study also specifically distinguished between traditional oil and gas structures versus other man-made features like shipwrecks and wind turbines. Was the impact the same across the board?
No, not at all, actually. The presence of wrecks and, interestingly, wind turbines appeared to have a greater local impact than the traditional oil and gas infrastructure did, at least for several key species groups. This included rays, sharks, sand eels, various flatfish, and demersal roundfish. Those are fish living near the seabed.
That's a really key distinction. The fixed, solid, submerged foundation of a wind turbine or a sunken ship acts very differently physically than, say, the open lattice structure of a massive platform jacket.
Exactly. And the strongest positive association with wrecks specifically was found for large piscivorous sharks, so fish-eating sharks, and also for sole and thornback and spotted rays. It seems wrecks create these complex, hard substrate habitats that are just highly favored by those particular species. They provide shelter, maybe feeding opportunities.
Okay, but the reverse was also true, wasn't it? The infrastructure isn't some kind of universal benefit out there. It's not all good news for every species.
Certainly not. The statistical models also found clear negative associations. For example, sand eels, haddock, and turbo all showed a negative association with platforms. Perhaps it's the noise, the operational movement, maybe the physical structure itself just acts as a deterrent for those particular species. We don't know the exact reason, but the association was statistically significant. Conversely, though, we saw halibut showing a strong positive association, but only when they looked at the combined category of platforms, pipelines, and cables together. So the main takeaway here is that every piece of infrastructure seems to act as a highly specialized, very localized habitat, or conversely, a localized deterrent. It's not one size fits all.
Okay, so we have confirmed that human structures do create these fascinating localized artificial reefs and habitats or avoidance zones. But when CFAS zoomed out, when they looked at the entire North Sea ecosystem model, they reached a pretty powerful conclusion about ecological priorities, didn't they?
Yes, this is probably the biggest insight from that ecological modeling work, and it's the one we really need to sit with for a moment. While the local ecological effects of these man-made structures are definitely confirmed, and they certainly matter greatly to those specific species, especially non-commercial species perhaps of conservation concern, the modeled effects of all that infrastructure on the ecosystem as a whole are ultimately considered minor.
Minor. Okay, minor compared to what, though?
Minor when compared to the potential effects of broader, often unmanageable environmental pressures. The study specifically highlighted two major pressures as examples. One was an increase in sea temperature, a direct result of climate change, and the other was modeling what would happen if fishing effort were to increase back up to historic, much higher levels seen in the past. Those kinds of large-scale pressures fundamentally shift the entire food web, potentially impacting everything, and their effects in the models dwarfed the localized impact of the fixed infrastructure.
Right, so our deep dive today has synthesized these two incredible, almost parallel realities of the North Sea. On one hand, you have it dominated by these ancient, massive geological forces, those millions of years old Sinkites, which, as we heard, directly impact very modern energy goals like the security of CCS.
And the other reality is the present-day ecosystem, which clearly adapts to human structures, but in highly specific, localized ways. Even though the overall influence of that infrastructure seems to be consistently overshadowed by these much larger, widespread environmental pressures like global temperature shifts or potential changes in fishing.
This tension, it really forces us to confront a pretty profound strategic question, doesn't it? We spent huge resources, time, and money analyzing and managing the fixed local impacts of our infrastructure. The precise safety rating of a pipeline, the ecological survey around a wind farm, the massive costs and complexities of decommissioning an old platform.
But if the sheer, often unmanageable force of natural variability, whether that's geological upheaval from ancient times creating structures like Sinkites or massive environmental shifts like temperature change happening now and into the future, if that far outweighs the fixed local influence of our structures, does this reality maybe change how we should prioritize our conservation efforts, our investment, our focus?
A really tough question of agency versus scale, isn't it? Should we be more concerned with managing the massive, gradual, widespread shift in the environment due to global climate change, something that feels almost too big to handle sometimes? Or should we perhaps focus our conservation efforts more sharply on protecting those subtle local habitats, the specialized homes that are created by the fixed infrastructure? Habitats that are directly subject to our decisions to build or, crucially, to decommission them.
Yeah, that tension between the human choice to create or remove these local habitats and the much larger planetary forces that ultimately dictate the overall environment, that's a really powerful thought to consider the next time you maybe look out at that vast, vital, and incredibly complex body of water. Thank you for joining us for this deep dive.
Absolutely. Some fascinating insights today. Until next time.